All right, folks, why don't we get started? Nice to see people here again, and nice to see people joining us online. I see people are still trickling in. We're good over 100 people here with us online, though. Numbers growing and growing. Um, we're going to pick up where we left off after quite a break. Super happy to be back in class, where we're supposed to be, right? Teaching you guys and talking about chemistry. What else could we do that's any better than that? Um, One thing I do want to say is definitely we have a bit of a change of schedule kind of foisted upon us because of this 1 month gap in what we're doing. Um, Before I say much more, just online people, quick thumbs up or thumbs down in the chat if the sound is okay. If I'm too loud or too quiet, let me know. And hopefully that looks okay. Or if you can't hear me at all, let me know. Okay, so we have to change a couple of things about the course. I'll tell you this right away. I haven't made up 100% of my mind exactly how everything is going to change, but I'll tell you sort of my guiding principles. First thing is, we are in no race. I'm not attempting to cram everything from the whole semester into a smaller package, if you know what I mean. So I don't know, did you guys get an email regarding how the term is changing? Yeah. And so what they decided to do was add 3 more days. Thank you, people in the chat, for the thumbs ups. So they added 3 more days onto the term. And I think it pushed a few dates back by a couple of days. No radical change, though. Like, we're not going into May or anything like that. Convocation still happens at the same time. Um, and I think I worked it out. It means for us, we have 6 fewer classes than we might otherwise normally have. Um, Obviously, too, it pushes us a month out. So here's my plan for you folks is I put a survey out actually for one of my other courses, and hearing the same thing from all of my students in that course, and it's probably true for most of you guys as well. The most important things people had with respect to sort of picking things up and continuing, first of all, don't try to pack in too much content in the remaining time. And definitely that's not the goal. Second, don't just start canceling all the assessments. So people were worried that if we cancel a midterm, cancel the exam, cancel assignments, and so on, there's not very many things to base your grade on anymore. So my plan isn't to do that, but what I do plan to do is increase flexibility. I'll say it that way. And flexibility in 2 ways. One is in terms of how you are graded. I think what I'll do is come out with some marking schemes that maybe are different ways of adding things together for you in this course, so that I could mark you, say, 3 or 4 different ways and give you whichever one is best, for example. I could, make things optional, things along those lines. I kind of want to keep it more like that, where I'm not going to cancel any activity outright, but there may be an opportunity, if you can't do it or you just can't handle it or whatever, to have your grade shifted to something else. But if you want to do it, you can, you know. So I will send this by email. It's harder to say just out loud how exactly it's going to look, just because I have a tendency not to exactly remember what I said. I know it's recorded, but still. I'll send an email that's kind of laying out exactly how this is going to go. In the near term, though, there are a few things that I can comment on. One was the previous unit that we finished right before the strike was the unit on elements of chemistry, kind of history of chemistry, this kind of stuff. There was a unit assignment that was posted for that one when we started that unit, and it had a due date originally, I don't know what it was, February 6th or something. It was like very early in February, a couple of days into the strike. And what I noticed is most of you had already completed it. Like around 70% had already done it, but several had not. And so what I've done is I've moved that due date to March 10th. And that's 1 week from today, right now. And usually, remember what I do is when I finish a unit, you get 1 week to complete those unit assignments. So this, we're going to restart the clock as of today, and you have 1 week to get that next one done from the previous unit. We're starting a new unit today, which you can, well, if you're online, you can't see, but you will in a bit. Here, look, I'll switch it up so you can see my slide here. The next unit is going to be on air pollution. In fact, we have 3 units on air pollution, different aspects of air pollution that we are going to handle. The unit assignment for this one is now live. So you can start this one. Come on in. Yeah. You can start this today. And I haven't set a due date for that yet because the due date will depend on whenever we finish this unit in class. The other one is assignment 1 had an original deadline, I think it was February 18th, which fell right in the middle of the break. I checked numbers just before class. I think I have like 35 submissions, which is actually less than 10% of the class. We have 359 people in the class. So we're just a little under 10% there. So obviously that deadline is gone. I've created a new deadline for that, which is March 17th. You may have noticed if you looked at that at all over the strike break, it had a deadline there of March 18th. It said February 18th, and then if you looked at the actual document, it was March 18th. And the reason why that happened is the night the strike was called, I went in and I just changed the date so that it wouldn't close, so that if anybody wanted to submit over the strike, you could. But I didn't change any of the text or anything like that. I knew it was pointless to change a deadline when I didn't know when we're going to be back. But now we are back, and we can use our new deadline. And the new deadline is, again, March 17th. So I changed the text on Acorn, and I've changed the deadline there. So that's another 2 weeks from today. So please, yeah, take a look at that. Usually what I do for this course is have a second assignment, which is, seems like every year, for the last 2 years, this one's always been like, because 2 years ago was when COVID kind of started in March. And then that caused us to like, everyone had to go home like right away. People like were told, this is your last night in res, go home tomorrow, this kind of stuff. So that got kind of canceled that year. Last year, it was hard because they're kind of like group assignments, and with COVID was kind of, peak, I think, around now. I don't know. Let me rethink what's going on with our second assignment, but I would like to at least have that as an option for you folks to do. So more on that in the future. Midterm. So midterm is the other thing. I forget what our original midterm date was supposed to be, but maybe we didn't have a midterm, did we? No midterm, right? So yeah, I'm not going to give you a midterm then. Exam. Final exam is the big one because this is a big class. What's going to go on with the final exam? I think what I'm going to do, I'm going to make it an online exam, and I'm going to make it like choose your own adventure in a way. Like I'll leave it open for a while, and you can pick when you want to do it. So that way, I don't know what this is going to do to your exam schedules, this reshuffling. If you have a bad schedule, I don't want to throw Chem in Our World into the middle of your schedule and make it worse. So usually what I do is I have the exam open, like, there's like 2 study days. I can open it like that early. That way, if you want to do it like immediately and not never have to think about it again, you can do that if you want. Otherwise, just pick any time during the exam period. And I'm going to tell the registrar's office, no, I better tell them we have a scheduled exam. Otherwise, people might leave, or I don't know. So I will tell the registrar's office we do have an exam. Maybe I got to think about before I make that promise, because I also don't want to complicate your schedules, because it complicates the exam schedule if I fix a slot for 359 people, and there's no need because we're not going to be running it in person. So yeah, I'll make things easy for everybody here. What else? Well, these unit assignments, first of all, if you remember how I'm grading these, the promise at the beginning of the course is that there will be 100 questions total before the course is over. And I don't know how many in we're at. I think we're probably around like 30 or so. And my guess is that we're not going to get to 100. So my plan is to still get to 100, but there might be like kind of an assignment at the end with a chunk of questions that you can do, and it'll be kind of like bonus. I'll explain it in email. So bottom line, I'm going to be very flexible with you folks, as much as I can be. Sometimes hard with a very large class to just let anything go. We're not going to try to cram more material. We're going to proceed as we have been with fuzzy deadlines from here on in. Cool? Awesome. People are with me? Is it a take-home exam? No, well, I mean, it's online. It's going to be an online exam through Acorn. So you could take your computer home with you and write it there. You don't have to write it in the gym if that's what you're asking. Or if you want to fly to Calgary and write it there, you can do that too. It doesn't matter. Like, you don't have to physically be here. Yeah. Good. So let's start our next unit, which is on air pollution. Very important environmental topic. Air pollution, there's very many elements to it. We're going to focus on 3. The first one is going to be the air close to where we are, like the air that we breathe in every day, and the kind of pollution that we put into the air and how that might affect our health, and how that has looked and changed over the years. One thing I'll say right up front is right now, you are probably breathing the cleanest air that exists in the world. You know, Nova Scotia has extremely clean air, probably the cleanest air around the cleanest air in Canada, and Canada has around the cleanest air out of any country in the world. And you can sit very, very comfortably knowing that, you know, we have very, very good air quality here. Also, I was told in this classroom we have like super good air handling units, because that was a concern for COVID with this number of people in this space. So yeah, you got very fresh air in this room as well. So we want to think about this a little bit more. And you know, sometimes if you're sitting down and you're looking up into the sky and you're looking at the clouds, they look so far away. Or you see a tiny little plane, you know, and you can see like the vapor trails behind it, and it looks so far away. It looks like a tiny little dot. It just makes you think that the atmosphere is sort of infinite, you know what I mean? Like it just kind of goes forever. It's unimaginably large. But if you look at the Earth as a whole, the atmosphere is actually super, super thin. And you know, here's a picture of our planet. This is a very famous picture of our planet. I think it was the first picture of the Earth which had the entire Earth shown with no shadowed parts. So in order for this to happen, the sun has to be directly behind the camera. You can't use a flash and, you know, take a picture of the Earth that way. And here's a close-up, and what you can kind of see is at the edge of the Earth here, there's almost like a little bluish haze. And that bluish haze is the atmosphere. And you think about how thin that looks on this picture relative to the whole size of the Earth here. I've heard it described as almost like, imagine an apple, and the atmosphere is like the peel of the apple in thickness compared to the size of the apple. So it's not like we can just dump crap into the atmosphere and have it just go away. We're actually dealing with a limited volume of air, and our activities here on Earth can have profound impacts on the quality of the air in our atmosphere. Our atmosphere is broken up into different layers, and you may have seen something like this before, but we call the layer, it starts at ground level and goes up to about 10 kilometers. We call this the troposphere, and this is the layer closest to the Earth. It's the densest layer. The atmosphere gets thinner the higher up you get. And it's the part of the atmosphere where all living things can be found. Almost all living things. Like I guess, if you have like a International Space Station, there's some living things that are not part in the troposphere, but you know what I mean. It goes up to about 10K. You can see Mount Everest, little picture here. Give you an idea, tallest mountain in the world, how close it comes, almost comes to the top of the troposphere. And then above the troposphere is the next layer up, which is called the stratosphere, then the mesosphere, thermosphere, exosphere. The way they define the layers is based on temperature, actually. So if you start going up in altitude, if you start climbing up the side of a mountain, I'm sure you've seen this before, many mountains have snow-covered caps, even if it's in a warm tropical area. Because the air gets colder, the higher up we go in elevation. And that's true until you get up to around 10 kilometers. And then what happens is there's a switch, and if you start going higher elevation than 10 kilometers, it starts to get warmer again. And you can see in this graph, that red line that you see here on the right, that's the temperature. So it's getting lower, 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 until it gets to about this point. And then it starts to increase again. So the point at which it stops decreasing is the point where the troposphere becomes the stratosphere. Then it switches again up here, and then it switches again up here. So when the temperature switches from going up to going down, that's when we sort of mark the barriers between the different layers of the atmosphere. All right, so what's in the atmosphere? Obviously air. Air is what we breathe right now. And chemically speaking, there's two main gases that make up the air that we're breathing. The major one is nitrogen gas. And it's just a molecule with two nitrogen atoms stuck together. And it makes up around 78% of the air that we breathe. Almost all of the remainder is oxygen gas. And oxygen gas, we know, is what we breathe. It's what plants produce. And we need it to do our bodily metabolism. And plants produce it as a byproduct of photosynthesis. And then all of the other gases that are in the atmosphere total up to around 1%. So what are some of these other gases? Well, the most important, the third most abundant gas in our air is actually argon, which is one you don't hear about all that often. It doesn't really have much impact on our health or our lives or anything like that. Argon is a noble gas. Argon is not very reactive, doesn't really react with anything. It doesn't really have much consequence that it's in the air, which is why we don't really talk about it or think about it all that much. But it makes up almost 1% of the air that we're breathing in right now. So there's all kinds of argon around. Makes up 0.9340%. The fourth place gas is carbon dioxide. And carbon dioxide is the one you hear about all the time. Carbon dioxide is the one that has the bad rap for global warming. Carbon dioxide is what we exhale. Carbon dioxide is what you get when you burn fossil fuels and gasoline. And carbon dioxide is what plants take in. So, it's certainly extremely important as a gas, as a component of our atmosphere. However, it only makes up a tiny fraction. It only makes up around 0.04% of the air that we are breathing in right now. So it's small but mighty, extremely important, but present only in very tiny amounts. Then there's a whole bunch of other gases, methane, some noble gases, neon, helium, krypton, hydrogen's in the air a little bit, in very, very, very low amounts. If you go down below there. So the big four, number 1 is nitrogen, number 2 is oxygen, number 3 is argon, and number 4 is carbon dioxide. You recognize the food babe? Remember her? We talked about the food babe quite a bit back a month ago. Well, she's back. She gives advice like this: if you're traveling, the air that you're breathing on an airplane is recycled from directly outside your window. That means you're breathing everything the airplane gives off and is flying through. The air that is pumped in isn't pure oxygen either. It's mixed with nitrogen, sometimes almost at 50%. To pump a greater amount of oxygen in costs money in terms of fuel, and the airlines know this. The nitrogen may affect times and dosages of medications, et cetera, et cetera. So yeah, it's definitely, I mean, she's correct that it's not pure oxygen. Pure oxygen would be extremely dangerous to fill a cabin with. What they're pumping in is actually air, which is like around 21% oxygen. So she should take this course and then learn, among other things, what the correct composition of air really should be. You can actually breathe in air that has a higher concentration of oxygen. If you have like respiratory problems, for example, like COPD, you may be put on oxygen and you're breathing a greater concentration because your body's ability to take oxygen out of the air may be compromised. Or you can buy this stuff, which is called nitrox. And nitrox is used if you are a scuba diver. And the idea there is if you're going underwater and you're diving and you have your tank of air, you want to have a higher amount of oxygen in it because you don't want to have to carry more gas than you need to, right? So you don't need the nitrogen, except if you breathe pure oxygen, it can be very, very bad for you. So nitrox is 36% oxygen, almost double the amount that's found in air. And I think before you're allowed to use this, you need like training and a course and a certification and stuff like that. All right, so we're going to go back to a little bit of some more basic chemistry here. Last unit, we had discussed the structure of atoms, and we said there's protons and neutrons in the nucleus of an atom surrounded by a cloud of electrons. A molecule is basically just two or more atoms bonded to each other, stuck together somehow. And oxygen and nitrogen, which are the big two that we're going to be breathing in right now, are what we call diatomic molecules. So diatomic just means there's two atoms in each molecule. So you can see here we have oxygen. Oxygen, sometimes we call it O2. It's just a molecule that's made up of two separate atoms of oxygen bonded together. So sometimes we would call these things either compounds or molecules. I think compounds is if there's different types of elements, like CO2 might be a compound. But molecules is sort of it's a single unit, but it's made up of multiple atoms bonded to each other. Other gases, like the noble gases in particular, exist just as single atoms. They don't have bonds. They don't have more than one atom. We would call these just monatomic gases or something like that. All right, every time I talk, like my mask like slowly migrates down, so I'm just adjusting it for that reason. Although I wonder, it's what is it, 2 weeks before all the mask restrictions are gone in Nova Scotia? I suspect we'll probably keep them for classrooms here for a little longer, but we'll see. And so in terms of what these gases look like, if you could like zoom in and look at them at the molecular level, the difference between a gas, a liquid, and a solid kind of has all of the particles, all the molecules stuck together. They're in contact with each other, and they're kind of in fixed locations. So the molecules can't really migrate through the material. They're kind of stuck in one place. And so this is an example. These molecules that you see in this picture are water molecules, H2O, where the red thing is the oxygen and the yellow things are the hydrogens. White things are hydrogens. So they're all in fixed locations. If you melt the ice to make a liquid, again, you still have a very high density. The particles are all still close together. They're all still in contact with each other, but they can kind of move independently of each other. They can travel through kind of the mixture. With gases, the big difference with gases, you have all of these big spaces, you know, between, might be another one down here somewhere. All these big spaces between atoms, and it's just empty space. Like there's nothing filling up that empty space between these molecules. So I guess that's one way we could define a gas, is it's a phase of matter where there's huge distances of empty space on average between any molecules. And these things are moving around. They're moving fast. They're constantly smashing into each other, smashing into the walls of the container. If they're in a balloon or something, they're hitting the walls. But on average, if you could like take a snapshot, freeze everything and just look, there's going to be these big gaps between all of the molecules. All right, so as I indicated, the first unit quiz is open. And the question says, what gas is the third most abundant in air on Earth? And I've listed the top 4. O2, CO2, argon, and nitrogen. What's number 1? Nitrogen's number 1. Number 2? Oxygen. Number 3? Argon. Yeah, argon is the third most. CO2 is next. Kind of a distant fourth. It's only 0.04%, where argon's almost 1%. Number 2, which of the following is not one of the 4 states of matter? We have a plasma, we have a liquid, we have a gas, we have a solid, and we have air. Last one, yeah. Air is not a state of, well, I mean, it is a gas. Air is a gas. Air refers to the specific mixture of gases that we breathe here on Earth. All right, so these the way gases behave and the way they respond to things like temperature and pressure was some of the earliest chemistry that was ever done. And if you remember, we did a kind of elements of chemistry unit, and all those guys were, you know, making elements and all that kind of stuff. Around the same time, there was scientists that were investigating how the properties of gases changed if you were to change the pressure and change the temperature and things like that. And the first one here is Charles' law. And what Charles basically did, I don't know what the first name was, is measured how much volume a gas would take up if it was put in a flexible container like a balloon. And then change the temperature and measure the volume again, and then change the temperature and measure the volume again. And what he found is that there was a straight line relationship between the temperature and the volume of that sample of gas. And you know, it kind of makes sense. They're directly proportional, I guess is the way we would say it in math, meaning if you double the temperature, you will double the volume. And when I say double the temperature, I'm going to be very careful with how I say that, because in chemistry, the scale we often use for temperature is called the absolute temperature scale. It's in units of degrees Kelvin. It's a little different than Celsius or Fahrenheit. 1 degree Kelvin is the same increment as 1 degree Celsius, but the 0 starts at a different point. Kind of like Fahrenheit and Celsius have a different 0 point. Like 0 degrees Celsius is where water freezes. That's equal to what? 32 Fahrenheit, I think? Yeah, ish, I think. Something like that. So what Charles did is, you know, he took this gas and he drew this straight line, but then he like continued this line backwards. Kept going and kept going and kept going. And what he found was no matter what gas, this is gas A, this is gas B, no matter what happens, if you keep going all the way back, they all hit 0 at the exact same point. And so what the assumption was, what he assumed is, well, if the gas becomes 0 volume at that temperature, that's the coldest temperature that can exist, because you can't go to negative volume. Therefore, this must be the bottom of the temperature scale. And this is now called absolute 0. And it's equal to negative 273.15 degrees Celsius, which is often called 0 Kelvin, 0 degrees Kelvin. So the 0 of that Kelvin scale, the absolute scale, is based on this Charles law relationship. So this is kind of a neat thing. It's actually like quite true. I have a friend who grew up in northern Saskatchewan, and in the winter, she said it would get extremely cold. It would get as low as like negative 40, negative 50 sometimes. And she said what would often happen is she would get up in the morning to go to work, and she'd turn on the car, and when she'd start driving, the tires would go like bump, 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 bump. And what was happening is the tires, because they were so cold, the volume decreased, and the bottom of the tire went flat because it had the weight of the car on it. So it kind of had they weren't round anymore. They were round until you got to the bottom and they were flat. And then the other thing is if you take rubber and you cool it down, it gets a little less flexible and it gets a little brittle. Not brittle per se, but it gets kind of hard. It doesn't bend as easily. And so what you do is you drive, it had that flat part of the tire that she kept hitting every time she'd roll over the tires. And she said after you drive for a kilometer or so, they warm up, they kind of expand, and it's like driving normally again. But it was just one of these things that you kind of had to deal with. Anybody ever lived somewhere extremely cold like that? I know a lot of people might consider where we are now extremely cold, but no, this is nothing. It's balmy. Beautiful. Boyle's law is another one. He's a guy who came along and he was looking at the relationship between pressure and volume. And basically what he said is if you double the pressure on a gas, the volume will decrease by a factor of 2. So there's this inverse relationship between them, between pressure and volume. So what else is in our air? We talked about these 4 things. There's clearly more than just these 4 things that are present in our air. The next big one, and maybe the next most important one, Bailey says Ottawa. I lived in Ottawa. So that was in response to my question, have you ever lived somewhere extremely cold? I've lived in Ottawa myself. It is much colder than it is here in the winter. I moved in January. I moved from the West Coast, which barely goes below 0. And I was soft. I was used to basically 4 winters with no winter. And then I moved to Ottawa, which the first 2 weeks I was in Ottawa, it didn't warm up above -20. So it was in the -20s, and I think it went below -30 a few times for the 2 solid weeks. It set a new record that year for consecutive days of the canal being open for skating. I think it's been beaten since. That was 2004, I think, is when I was there. And I think they just beat it 2 years ago again. So yeah, Ottawa's cold. And super hot in the summer. It's much more extreme. I'm used to Nova Scotia, where it's not that hot in the summer, not that cold in the winter. So the other gas that can be present in our air is water vapor. Water vapor, I didn't include it before because the amount of water that's in the air is highly variable. It can go anywhere from 0%, which is what you'd find in the desert, to 5%, which is what you'd find, on a really rainy day here in the summer. So we usually talk about the amount of water vapor that's in the air in terms of humidity. So if we say there's 100% humidity, what we mean is there's 5% water in the air. And then if there's 50% humidity, it's 2.5% or whatever. So often when we talk about the composition of air, we forget about water because it can vary so much and based on where you would go. All right. Water, we know the structure of water, right? Davy gave us the formula. How did Davy find out what the formula of water was? We're reaching back now. Humphrey Davy. Yeah, somebody. Yeah, exactly. So he just took water, took a battery with 2 wires and stuck them in and collected the gases that came off the electrodes. And he found one of the gases on one electrode was oxygen, the other was hydrogen, and they were produced in a 2-to-1 ratio. So we thought water must be a 2-to-1 ratio of hydrogen and oxygen, which we know it is. We know the structure as well. It has this sort of bent structure where this is a hydrogen, this is a hydrogen, this is an oxygen, and it has a bond angle of 104.5 degrees. If you were to look at that angle right there. We call the structure bent. We're very, we've got very descriptive names for shapes of things. It's bent. It looks like something that you just bent like that. All right, we already talked about atomic structure before. I'm not going to talk about that. But I do want to talk about bonds. I talked about how these atoms are stuck together in a molecule like N2 or O2 or H2O. Why do atoms stick together? This is a primary thing we talk about if you take like first year chem, or I'm teaching a 4,000 level chemistry course right now. It's called Structure and Dynamics in Organic Chemistry. And we spent like the first third of the course already talking about how things bond. So it's a very complex topic, but essentially it's this. We call molecules, the bonds are pairs of electrons that are shared between two atoms. And atoms like to have all of their electrons paired, and they like to have certain numbers of electrons, and in order to reach that number that they want, and to reach pairing all of their electrons, they often have to resort to sharing electrons with other atoms. So if you take a molecule, like an atom like hydrogen has one proton in the nucleus and one electron. If you make a molecule H2, what happens is one electron from one atom gets together with another electron from another atom to make a pair. And that pair is sort of held between two separate atoms, and that pair that's held between the two of them is what we would call a covalent bond. So covalent bond just means a pair of electrons that's being shared by two separate atoms. And they're almost, you can think of it like they're both holding on to the electron pair at the same time. And so they're kind of like, you know, tug of war, you know? It's almost like those pictures you see on TV where there's like a sale, and there's two people that grab the last item at the same time, and they're both like pulling on it at the same time. So kind of like that. Like the two atoms are pulling on that pair of electrons. They both kind of want the pair, but neither will let go. So that they end up being stuck together and held with each other. Was that a pump thingy? Where was the pump thingy that I was talking about? This? Maybe. But yeah, this is just a container with like a lid that you can like squish down. You call that a piston. All right, so covalent bonds, if you look at the periodic table, and this is a picture of the modern periodic table, remember this bottom part here should be inserted up there and the whole thing made wide. It's these ones that are in yellow, which are elements we call nonmetals, which are the ones that make these covalent bonds most commonly. All the other ones, all the blue ones are metals, and all the blue ones bond in a different way. They don't do covalent bonds typically. I mean, there's rare cases, yeah, but in general, it's the yellow ones here, the non-metal ions or atoms that form these covalent bonds. And you can see the important ones here. There's carbon, C, nitrogen, oxygen, noble gases, phosphorus, sulfur. These ones are called the halogens. We've got hydrogen. There's fluorine, chlorine, bromine, iodine, acetine. Those ones all like to form bonds, and these are actually essentially the most important elements for forming molecules in our bodies as well. Carbon especially, then probably hydrogen and oxygen, nitrogen as well. It's in all our proteins. The green ones that you see that are kind of straddling that line, sometimes we call it a staircase. Those green ones are sort of intermediate in their properties between metals and nonmetals. They'll often form covalent bonds too, but kind of everything that we associate with metals and everything we associate with nonmetals, these ones are kind of intermediate. So what do I mean when I say that? Like, think of a piece of metal. You got a piece of iron or a piece of copper. What do we know about metals? Well, they're not brittle. You can typically drop a big piece of metal and it'll just clang around. It won't shatter. They can be pounded into different shapes. They can be stretched into wires. They can conduct electricity and they can conduct heat. And compare that to like a piece of plastic, which is sort of the opposite. A piece of plastic can be very brittle. It can shatter, you know, if it's cold. It's an insulator. It's what we wrap wires in so that we don't get electricity moving through it. These green ones are kind of half and half. So these might be things we might call semiconductors. They kind of conduct electricity, but they're not great. So like silicon is used in microprocessors as a semiconductor, things like that. All right, so each element will have a specific number of bonds that it will prefer to make so it can reach its magic number of electrons that it wants to have, based on rules in quantum mechanics that if you take first year chem, you can learn all about. So these ones, hydrogen, fluorine, chlorine, bromine, iodine, all like to form one bond. And I'm kind of comparing these to a piece of Lego, right? Like if you have a piece of Lego like that, it only has so many, what do you even call those little bumps? It can only make so many bonds that way. Oxygen and sulfur prefer to make 2. Nitrogen and phosphorus, 3. Carbon and silicon, 4. These ones I have in brackets. The reason they're in brackets is there's lots of exceptions for those. But yeah, this is sort of it. You can actually tell from the periodic table how many bonds they're likely to make. So like group 8 here makes 0 noble gases. Halogens make 1. Oxygen and sulfur makes 2. Nitrogen and phosphorus makes 3. Carbon and silicon make 4. So you can go to the periodic table and you can count over from the edge to figure out how many bonds each of these atoms, each of these molecules is likely to be making. Cool, and you may have seen these molecular model kits as well, where you get these little balls, and each ball, based on its color, is going to be a different kind of atom. Black is always carbon, hydrogen is always white, oxygen is always blue, and these have holes. And the number of holes they have is the number of bonds they can make, and you can use these sticks that are in the kit to, represent the covalent bonds, which are electron pairs that are being shared. And these are kind of nice, like if you give them to even like kids and they start building them, they can kind of get a feel for what molecules are possible structures just if you fill all the holes of all the atoms that you're using, it's going to make a stable molecule. And we can do the same thing on paper. Like we can predict structures of molecules that are likely to be stable and ones that are likely not to be stable based on some very basic rules. All right, so that's how we can tell the number of covalent bonds. These ones don't do covalent bonds. These ones do something else. It's called metallic bonds. I said bombs. I meant bonds. So carbon likes to make 4. So how does that look? If you take a molecule of CO2, it has 2 bonds to one oxygen, 2 bonds to another oxygen for a total of 4. This one is methane. Methane makes 4 bonds to hydrogens. Hydrogen only likes to make 1, so you can make hydrogen happy and carbon happy by making a structure like this. This is something we're going to be talking about in our next unit. This is a freon. It's a CFC, chlorofluorocarbon. This one is it's called acetylene. It's often used in welding. And you can see carbon there has 4 bonds. It's making a triple bond, 3 bonds between 2 carbons. So you can have multiple bonds between atoms as well to get them to the number of bonds that they want to make, either with single, double, or triple bonds. Now, sometimes you can get molecules that make different numbers of bonds than what they normally prefer to make. And here's an example. Oxygen preferably makes 2. So if you have a molecule of O2, you get a nice stable molecule, 2 oxygens making 2 bonds. Everybody's happy. But if you add an oxygen atom, you can make a molecule of ozone, which we're going to be talking about in the future as well, where this has a situation where you only have a single bond between 2 oxygens, and the center oxygen makes 3 bonds. So those 2 don't have the ideal number, which makes them unhappy, which makes the molecule unstable. So ozone is much more reactive than oxygen is, much stronger as an oxidizer than oxygen is. Okay, a few more questions. A chemical bond that is formed by the sharing of an electron pair between 2 atoms is called metallic, covalent, a war bond or an ionic bond. Yeah, so this one is covalent. Okay. Ionic bonds is when you have two oppositely charged atoms that are attracted to each other because of their charge. Metallic bonds are what you have in a piece of copper or a piece of iron. But here we have covalent bonds. That means electron pairs are being shared between two atoms. Next, how many bonds does carbon typically make to other elements? 1, 2, 3, or 4? So this one's 4, right? And you can just count from the end of the periodic table in to where you find it, and that'll tell you where it is. So carbon, find it right there. Cool. We started at 1, didn't we? We got time. CO2 is another important one, and we kind of have a unit just on CO2 coming up in a bit just because of its importance in climate change. And, you know, it's around 0.04%. This is a small number, though, and what we often do with carbon dioxide is express it in different units. And often what you see for carbon dioxide is instead of using percentages, we use parts per million. So if you think of a percent is really parts per 100. So parts per million is when you have smaller amounts. So that equals about 400 parts per million. All right, this is just a neat little thing. It's I remember as a kid wondering how CPR could possibly work. That if you're like breathing into somebody who's like, you know, unconscious, like, didn't you already use the oxygen up? Like, how can you put air in somebody's lungs that way? Well, it turns out our lungs are not perfect at extracting the oxygen out of the air that we breathe. When you inhale air, it's around 21%, and when you exhale it, it's down around 16%. So we've extracted some of the oxygen out, but there's still a lot of oxygen left in the air that we're exhaling. We also lose carbon dioxide, of course. We breathe out carbon dioxide and water vapor as well. This comes back. Remember we talked about law of conservation of mass? And we talked about how if you lose weight, you are breathing out, literally, the carbon that you've lost that used to be in your fat molecules. Well, this is why, right? Like, every time you breathe in oxygen, you absorb oxygen and you expel CO2. So every breath, you're losing carbon atoms, which lose weight. And the more you exercise, the more metabolism you do, the more you breathe, the more CO2 you release. So I guess, you know, keeping weight in your body is probably better for the environment. Because when you lose weight, it goes out into the atmosphere and causes global warming. Probably not important, right? Okay, so yeah, we use ppm if it's much, much less than 1%. So carbon dioxide, this is funny, this says CO2 is 0.0385% of dry air. This is an old number. This is what it was like 15 years ago. We just keep driving this number up. So this one is over 0.04% now, and I don't know what the exact number is right now. But this number continues to grow every year. As long as we're burning fossil fuels, pulling carbon up from underground and burning it and putting it into the atmosphere, this number is getting higher and higher. So yeah, we talked about how that percentage can be converted into parts per million. It's around 400 now. There's a lot more than just this as well. In fact, anytime you smell something, you are smelling molecules that are present in the air in addition to those 5 that we talked about. Those 5 being nitrogen, carbon dioxide, oxygen, water, and argon. So when you smell something, right? If you smell freshly baked bread or a skunk or whatever, those are molecules that are being emitted by something that present in the air, obviously, that we're detecting. And typically, these are at very, very low concentrations. So our nose is actually very sensitive. And if you go through the animal kingdom, we're actually pretty poor on the scale of ability to smell faint substances in the air. Dogs are much better, bears are much better, lots of other animals have a much keener sense of smell than we have. So I want to talk about what some of these other gases are, and I want to talk about the ones of greatest concern. And so you see I've picked 6 different ones. I'm calling these major tropospheric pollutants. These are gases of concern that can be in the troposphere, which is the layer of the atmosphere where we live and the air that we're breathing in every day. And almost all of these are problematic because of human activity. If you go to someplace far away, far removed in nature, or you go back in time 1,000 years, formed through different processes. And I'm going to talk about each one of them as we go. That table that you see here in this scale, in this slide as well, is showing just guidelines from, I'm not sure if that's Environment Canada or Health Canada, but they're national guidelines that air has to meet to be considered safe to breathe. All right, so the first one we want to talk about is carbon monoxide. Carbon monoxide. So the name tells us there's a carbon and 1 oxygen, monoxide. And this molecule is just called CO. And we know it's kind of an unusual form of a carbon oxide. Normally carbon is carbon dioxide, CO2. And that's what you get when you burn most things in an abundance of air. So it produces mostly CO2 and water. However, if there's not much air available when something is burning, a little bit but not enough, it has a tendency to produce more carbon monoxide than carbon dioxide. So I think about this sometimes in terms of, like when we were kids, we had a wood stove at home, and you could load it up with wood, and it had this little like air thing you could pull in and out. I guess you can't see my hand, but you can pull it in and out to like choke. You could like put a lot of air in, and it would burn very quickly. Or you could like choke it back and it would burn very slowly with limited air. If there's limited air like that, you have a much higher likelihood of producing carbon monoxide. So when we do these chemical reactions, we talked about this back when we did law of conservation of mass, is a reaction has to be balanced. Meaning every time you do a chemical reaction, you can't create new atoms out of nothing. And you can't have atoms just disappear into nothingness either. All of the atoms that are present at the beginning are still present at the end of the reaction. All the reaction does is sort of reorganizes them or changes which ones are bonded to which. So here's an example of a carbon atom, which is what you might find in coal. And if you react it with O2, which is oxygen present in the air, they react to make CO2. And you can see here that there's the same number of carbons and oxygens at the end as there were present at the beginning. Carbon just kind of inserted itself in between the 2 oxygens. So yeah, all we really do is we transform the starting materials into the products. We don't change the amounts of anything. They all have to balance out. This is a sort of a fundamental, central, important idea in chemistry. All right, so here's one if you just burn carbon. Carbon is what you get if you burn coal, or charcoal is mostly just carbon. The balanced equation is just C plus O2 goes to CO2. Natural gas is another fossil fuel that we might burn, and natural gas is methane, which is CH4. It will also burn in oxygen, combined to make CO2 and water, like you see up here. However, in this equation that we have here, that's not a balanced equation. And you can tell it's not balanced if you just count up the atoms. So you can see on the left-hand side, there's 4 hydrogens in the CH4. In the right, there's only 2 in the H2O. So what we do is we put these coefficients in front. So what we're saying here by this equation is 1 methane plus 2 oxygens gives you 1 CO2 and 2 waters. So we put these coefficients in front in order to balance, to make sure that you have the same number and types of atoms on the left as you do on the right. So if we apply this to burning larger fossil fuels, like let's say octane. Octane is a component of gasoline in your car. And ideally, what happens is 2 octane molecules combine with 25 oxygens. They react, explode in the engine, push the pistons, make the wheels go, and you get 18 waters and 16 CO2s produced. They go out your tailpipe, out the back of the car. Great. However, if inside your engine you don't have the right amount of oxygen, if you have too little oxygen going in there, what happens, like let's say you choke it back. There's not enough oxygen, the reaction still goes forward, but instead of making CO2, it makes carbon monoxide. So anytime you burn something, and there may not be a huge amount of oxygen, carbon monoxide production is likely to take place. That's why in cars we have oxygen sensors. Anytime you have a car and like it says check engine or whatever, that's usually the oxygen sensor that's telling you the engine may not be receiving an optimal mixture of air and gasoline. Question 5. In order to balance the following equation, what number must go in the blank? So these are something that we do early on in chemistry, put these coefficients in to make these things balanced. In this case, what you can see on the left-hand side, we have 2 hydrogens, 1 oxygen, and some amount of sodiums. On the right, we have 2 hydrogens, 2 hydrogens. There's 4 on the left, 4 on the right? Because there's 2 times 2H and H2O. 4 on the left, 4 on the right. There is 2 oxygens here. I should just start this slide all over again. All right. How do you count this? This 2H2O means there's 2 water molecules. So 1 water molecule has 1 oxygen, 2 water molecules has 2 oxygens. 1 water molecule has 2 hydrogens, 2 molecules have 4 hydrogens. And then there's some sodium. On the right side, NaOH has 1 oxygen, 2 NaOHs has 2 oxygens. NaOH has 1 hydrogen, so 2 of them has 2. Plus there's an H2. So you take the 2 from H2 and add it to the 2 from NaOH for a total of 4 hydrogens. And then there's also 2 NaOH, or 2 NAs, 2 sodiums from the NaOH. So in order to balance this, we need 2 on the left as well, and you can get that if you put a 2 in the blank. Okay? So going forward on tests and exams, like you may get balancing questions like this, but they're always going to be pretty straightforward. They can get kind of complicated sometimes. I'm going to make it so they should be pretty easy to count up. All right, so carbon monoxide used to be, I'd say, a much bigger problem with automobiles than it is now, mainly because oxygen sensors and the technology to get the right air ratio in there is much, much improved. Second of all, cars have something called catalytic converters that are in the exhaust line, so that if carbon monoxide is produced inside the engine, on its way out, it goes to the catalytic converter, which converts carbon monoxide to carbon dioxide using this equation right here. Just combines it with air to turn the CO into CO2, and that makes it much safer out the other side. So it used to be, I think, a thing where people would, one method people would often use to commit suicide is they would like lock their car in a garage and just run the car. And what would happen is it would produce carbon monoxide, they'd be breathing it in, and it would slowly cause them to go to sleep and die. I don't know if that, I wouldn't run your car in your garage with the door shut anyway, but probably in a modern car that would be a lot harder to do. It'd be impossible to do if you did it in like a Tesla, where there's no combustion at all in the car. That's funny to think, right? Like, I'm teaching all this about how gases are produced in vehicles. When I retire, this might be all obsolete, which is kind of cool to think, Like you guys might have kids, definitely grandkids, that'll be like, What's a gas station? You know, I just have no idea. I have things like that. It makes me feel old sometimes, like leaded gasoline. I remember as a kid, my parents buying unleaded versus leaded gasoline. You guys probably never had to deal with leaded gasoline. They used to put lead in gasoline. It made it burn smoother, but it also put a lot of lead into the environment, so it was kind of a bad thing. The biggest thing though, this is the biggest thing that ages me, is that when I was a kid, there was no internet. Internet was like first on the scene when I was in high school, and it was pretty established when I did my undergrad. And by grad school, it was like ubiquitous. It was funny how quick it came, actually. Like it was, within 5 years, it went from like nobody had heard of it to everybody uses it. Cell phones are similar. Like, I'm embarrassed to say this. I didn't have a cell phone until like 2012 or something like that. And I resisted getting one for a long time because I didn't want to be reachable at all times. I like the idea of just being able to like leave and then nobody could contact me. But it started to impact my life in other ways, so I had to get one. But yeah, iPhone 5 was my first phone I got. So I was late to the party too. You guys are probably thinking, iPhone 5s are ancient. Well, yeah, they are now, but anyway, I'm off track. So yeah, catalytic converters, they're at the bottom of the car. And they take not just the carbon monoxide, but also any unburned hydrocarbons, turn them into CO2, and it's great for the environment. They contain precious metals in them, typically platinum or rhodium, which are very rare metals, and they're worth quite a bit. There's actually a fairly decent black market trade for catalytic converters, where people will go under your car and steal your catalytic converter. And they're stolen not so someone else can install it. They're stolen because they can extract out the precious metals and then resell them. But these metals behave as catalysts, which are chemicals which cause another chemical reaction to speed up, but don't get used up themselves in the process. So they provide a surface for other chemical reactions to happen, but they themselves don't get destroyed or used up. We have catalysts in our body as well. We call them enzymes, very large, complex molecules, and we give them cool pictures like this. Yeah, Ryan says, worth a ton of money if you're looking for a quick buck. I'm just thinking, a piece fell off the bottom of my car like a few weeks ago, and it looks like that cover. So I'm pretty sure I have a catalytic converter still under there. Like, it didn't fall off because somebody stole it. Just the shield that holds it there came off. I should get that checked. So carbon monoxide is a health issue. If you breathe carbon monoxide in, actually physically what it does is quite interesting. CO as a molecule is very similar in structure to O2. And in fact, it sticks to our hemoglobin in our blood in the exact same place where oxygen is supposed to go. The only problem is it sticks there and it doesn't come back out. So it basically reacts with our hemoglobin and prevents our hemoglobin from carrying oxygen anymore. So if you breathe even like relatively small amounts of this, your ability to like oxygenate your tissues goes down, and obviously if you breathe too much of it, you can quite easily poison yourself. And this happens kind of fairly regularly, where people poison themselves accidentally with carbon monoxide. Anything in your home that burns gasoline or burns any fossil fuel at all is a potential source of carbon monoxide in your home. So that means fireplace, a wood stove, a lot of like appliances, like fridges and so on, can run on propane or natural gas. You can have propane stoves. You can have a furnace. You can have, propane hot water tank. Some people in the winter like to barbecue in their garage. That's a bad idea if the door is closed. All of these things are possible sources of CO that could potentially lead you to problems. And this is an example in Newfoundland from, what year was this? 2014. This was just a typical one that I picked, where there was a snowstorm and a power outage. And often what people will do in a power outage is go get their generator, feed that in so you can, charge your phones, keep your house warm, and so on. Problem is, with a generator, some people will bring them in the house and run them inside. And that's burning gasoline, and that's producing CO, which goes in the home. And you can see this is just one dead from carbon monoxide poisoning since the outage. Morgandy says Weird Al's parents died from carbon monoxide poisoning. I did not know that, but thank you for that not so fun fact, as she says, or he says. All right, I'm going to tell you a story now. It's a ghost story. Okay, this is a haunted house. It's a little sketchy. There's some like blood spots and stuff there. Let's turn the lights off to get the mood going. We're going to turn the lights down just a little bit. We're not going to make it super dark. We'll go to 30%. Okay, I can do that. We're going to go to off. Flashlight. That was pretty good. With the mask on, I was worried how this was going to go. So, yeah, this is kind of better for the online people too. So we're going to go with this. So here's the story. It says, so all the names in this, by the way, are just reduced to single letters. G, Mr. H, and I had not been in the house more than a couple of days when we felt very depressed. The house was overpoweringly quiet. The servants walked about on thickly carpeted floors so quietly that I could not even hear them at their work. So this is a family that's moved into a new house. One morning, I heard footsteps in the room over my head. I hurried up the stairs. To my surprise, the room was empty. I passed into the next room and then into all the rooms on the floor and then to the floor above to find that I was the only person in that part of the house. By the way, this is a true story. This is not fiction. It's a true first-person account. I had not been in the house more than a couple of weeks when I began to have severe headaches and to feel weak and tired. I took iron pills 3 times a day and spent a couple of hours each afternoon in my room lying down and resting, a rather discouraging process. After resting, my headache was always worse than it had been before. One occasion, in the middle of the morning, as I passed from the drawing room into the dining room, I was surprised to see at the further end of the dining room, coming towards me, a strange woman, dark-haired and dressed in black. As I walked steadily on into the dining room to meet her, she disappeared, and in her place, I saw a reflection of myself in the mirror, dressed in a light silk waist. I laughed at myself and wondered how the lights and mirrors could have played me such a trick. This happened 3 different times, always with the same surprise to me and the same relief when the vision turned into myself. As I was dressing for breakfast one morning, B, 4 years old, came into my room and asked me why I had called him. I told him that I had not called him, that I had not been in his room. With big and startled eyes, he said, "Who was it then that called me? Who made that pounding noise?" I told him it was undoubtedly the wind. And he said, "No, it was not that. It was somebody that called me. Who was it?" And so on he talked, insisting that he had been called and for me to explain who it had been. Some nights after I had been in bed for a while, I felt as if the bedclothes were jerked off me, and I've also felt as if I had been struck on the shoulder. One night I woke up and saw sitting on the foot of my bed a man and a woman. The woman was young, dark and slight, and wore a large pitcher hat. The man was older, smooth-shaven, and a little bald. I was paralyzed and could not move, when suddenly I felt a tap on my shoulder, and I was able to sit up. And the man and the woman faded away. Sometimes after I've gone to bed, the noises from the storeroom are tremendous. It does not happen every night. Perhaps a week or 10 days will pass, and then again it may be several nights in succession. Sometimes it sounds as if furniture was being piled against the door, as if china was being moved about, and occasionally a long and fearful sigh or wail. Saturday morning. I'll go back one. I'm just going to say this. Take this. We'll use normal light. This is a very common story. It was this was very similar to a lot of stories that people, first-person accounts of what it was like living in a haunted house. And you still see, what was it, The Haunting of Bly Manor, like shows like that, same sort of things. It's like moving chains, hear moans or wails or things like this. All the kind of things that people in popular culture associate with ghosts living in a house are what she's describing. Saturday morning on the 18th of January, G's brother told us that he thought we were all being poisoned, that several years before he had read an article which told how a whole family had been poisoned by gas and had had the most curious delusions and experiences. He advised us to see Professor S at once. As he was out, his assistant came to our house. We told him how listless and ill the children appeared. He found one of them lying on the floor and 2 others in bed. We related the experiences of the children and servants. He examined the house thoroughly from top to bottom and interviewed the servants. He found the furnace in a very bad condition. The combustion being imperfect, the fumes, instead of going up the chimney, were pouring gases of carbon monoxide into our rooms. He advised us not to let the children sleep in the house another night. If they did, he said, we might find in the morning that some of them would never wake again. So, let me get the light back on here. I should have left my flashlight on here a little longer. So, it was very commonplace to hear stories of haunted houses, especially in the Victorian times, Victorian era. And what's very interesting about those times is that that was a time when probably there was very, very poor safety standards when it came to things like stoves. The primary form of lighting back then would have been like oil or gas torches, like lamps, which could produce carbon monoxide. Probably in-home central ventilation systems were non-existent. So it makes sense that reports of haunted houses will be highest in situations where there's the greatest likelihood of there being carbon monoxide poisoning. It's now believed, actually, that perhaps all accounts, first-person accounts of haunted houses, were actually just reports of people who had carbon monoxide levels higher in their homes. So I'll tell you this. If you are ever living in a house and you start to feel that it's haunted, that there's you see signs of ghosts or all of the things that I'm describing, go outside and get fresh air and go get a carbon monoxide detector, which you can buy. You can find carbon monoxide leaks in your house. And yeah, find some other ways to live until you get that checked out. Probably not ghosts, just what I'm saying here. Okay, what do we have here? Porsche is working on synthetic fuels that can be as clean as an EV, according to Car and Driver. Internal combustion engines may be saved, and hopefully manuals. Okay, we got a guess on radon poisoning. We're going to talk about radon later. CO, yeah. Are CO detectors mandatory in houses like smoke detectors? I feel like it is becoming very common, especially in my hometown that is all old infrastructure. I don't think they're mandatory. Smoke detectors are mandatory if you want to have your house inspected or, it's like a required part of new construction, but carbon monoxide I don't think quite is. Not yet, at least. It might be in certain environments. I don't know. Yeah, so the answer to this one, by the way, is carbon monoxide, which is C. I'm trying to do the math in my head. We started at 1 today, right? So that means we go until 2:20. And right now it's 2:15. And we're just done carbon monoxide with a new unit to start. This to me makes it seems like a very logical place to finish up for right now. And then we can pick things up again on Tuesday. So keep your eyes open for an email from me, please, that should have an updated, I guess, set of deadlines and marking scheme and so on for this course. Great, thank you everybody for coming, for joining me either in person or online. I will continue to be offering these courses online and in person for the foreseeable future as well. All right, see you everyone. No problem, thanks for coming. It's nice to have people in person.